Hello, wonderful people of the internet. Welcome back to another episode of Simuleo's Kodo. Hey, thank you guys. Thank you so much for coming in. And anyone who might be lurking in chat, hey, thanks for being here. So today we're going to start with a bit of bookkeeping, and then we're just going to hop right into it and talk about what we're going to do today, why it's interesting, on all of that kind of stuff. So first things first, the bookkeeping. Keeping. All right. So I've decided that every Wednesday stream of mine is going to be a new segment that I'm just going to call Writing Wednesday or something. And the idea here is that every Wednesday I will be doing some sort of writing content on Twitch. The reason I want to do that is simply because, quite frankly, everything that I do when it comes to stream, everything I do when it comes to the algorithm archive with my YouTube channel is all related to programming. And don't get me wrong, I love programming. I'm not going to stop doing it anytime soon. But there is some level of, you know, if you put all your eggs in one basket, or if you just do one thing and that's the only thing you do, it gets a little bit tiresome. And the way I see it is I kind of want to branch out and do some other things as well. And one thing that I really, really love doing, and I can't imagine ever not loving at all, is writing. I love writing stories. And so I figure every Wednesday we can all gather around, have story time, not only with me, not only reading my stories, but also reading stories that you guys have read or written as well. Specifically, when we move on to NaNoWriMo, the National Novel Writers Month, there will be a lot of different people writing different things, and I think it'd be a good idea just to kind of collate them all into one session that we do every week, and I figure let's do it on Wednesday for alliteration's sake, and that's kind of the idea. Now, I did make the mistake yesterday that I accidentally streamed this in Science and Tech. I should have streamed it in either art or just chatting. That was my bad. I thought I did change it to just chatting, but I failed to do so that was my bad. Anyway, that's the bookkeeping, so let's go ahead and hop into what we're doing today. It shouldn't be particularly complicated. So as of the last time we did a ray tracing stream, that was, let's see, must have been this weekend, probably last Saturday. I ended up talking a lot about 3D ray tracing. All right, what I want to do is I want to do a 2D ray, I'm going to call it casting example, where here the idea is we have a single light source, which I'm actually going to color in, we'll say white here. And there's a bunch of objects, like a blue object over here, green object over here, red object over here. And some of these guys could be lenses, some of them could be a number of things. The point is, light will be emanating from this object and hitting basically everything, right? And the idea is, I just want to do a simulation where we can move this light source around. It's emanating light in all directions, and we can just show how light moves on a two-dimensional plane. This will be basically what we do for homework for the week that we do ray tracing, and then 3D ray tracing is what we'll do for lecture. So that's kind of how we're going to split it up to make sure that the lecture content doesn't overlap too much with the homework content. And so what I want to do today is just kind of get started on this 2D ray tracing example and see what we need to do to make it work. Now, I did this a long time ago. I don't actually remember how long ago it was, but it was certainly long enough ago that I don't remember any of the details to this. So what we will be working on today is just trying to remember exactly what the issue is here and how to get this working. So again, today's 2D ray tracing. Probably sometime next week will be 3D ray tracing. I will just very quickly mention that I am a little bit burnt out. I've been a little bit burnt out this entire week. I wasn't able to stream on Sunday because I had a meeting. I wasn't able to stream on Monday because, again, I had another meeting. And yesterday, well, rather Tuesday, I ended up just being too burnt out to stream. Wednesday, again, we did a creative writing stream just to get back into it. And today we're back into programming, but I am a little bit burnt out, so today's going to be a bit of a shorter stream. I'm going to just end at 8 o'clock p.m., even though I started a bit late. And that's kind of the idea. Now, I do, again, even though I'm burnt out, I'm sure today's stream will be great. It's just that I need to manage my own, I don't know how I want to put it, but I need to manage my own mental well-being, which is something that I have not been doing a particularly good job of since I joined MIT. Now, I have mentioned this before. I am definitely considering turning this thing that we're doing here, not just a Twitch stream, but also the YouTube channel, the algorithm archive, and everything, into a full-time job. And I'm incredibly passionate about that. The thing I'm burnt out of is basically doing programming for hire for other people. The thing is that because ray tracing is a part of this lecture series that we're doing, it kind of turns into this thing that I feel a bit I'm not particularly thrilled to do. Which is really weird for me. It's weird to think that there's some amount of programming that I'm not excited to do. But just because this is all related to stuff that I'm doing for work, it just feels like I'm doing work in my free time instead of it feels like I'm doing something cool in my free time. So that's the source of the burnout. I know where it is. I know why it exists. Now it's just a matter of dealing with it. Probably next Monday, I'm going to be spending all day working specifically on this lecture. I'm going to maybe stream, I don't know, maybe from 9 to 5. I have no idea. I'm going to do a long stream on Monday because it is a holiday. It's Indigenous Peoples Day, or if you are used to celebrating Columbus Day, it's kind of the same thing. Okay, so let's go ahead and hop in. Hey, Mika, how are you? And let's just do it. So CD project, simuleos. L is here, CD into ray tracing. I don't have that. I do have a directory called relationships, which I don't remember what it's about. So let's make a new directory here, and we're going to call it ray tracing. All right. CD project, simuleos, and now we're going to do ray tracing. Okay, so I have a lot of things that I need to think about. So the first thing I'm going to do is I'm just going to recreate some visualizations I did a super long time ago. So let me grab some of those visualizations, actually. I feel like I have a few already available. So probably it's going to be in geometrical optics. L is here. Let me just run make here. And let's just see what it builds. I don't know what it's doing. We're just gonna let it make an animation for us and see what it looks like, and then turn that all into an Ffmpeg. I don't know. We'll just see what happens. This is an old visualization scheme that I did a long time ago. Just so again I have some sort of visual flair on screen. I like to have an animation in the upper left-hand corner of what it is that we're trying to do, just so people have an idea. Let me get some water. And so again, like I said before, we do have a definite, like we have some code that we can look at in case everything goes awry. So it should be okay, worst case scenario. Again, I hope you guys are all having a wonderful day. If you guys have any comments, questions, concerns, ideas, anything like that, feel free to let me know, and I'll totally address it as soon as I see it in chat. I've got HTOP up here over on the left-hand side because potentially when we're doing this visualization, I may have been using the convert function. Right, good. So if I do here, ls, we should have, it's all temp.png, so I'm going to do ffmpeg. Actually, let me just do ls dash temp, oops, sorry about that, star.png, and let's see what we have here. So it's just image 00. Okay, so if I do ffmpeg dash I, temp, let's do 05, I think it's percentage 05d .png, and now we're going to do out, and we're just going to call it out.mp4. Let's see what that does. Is it going to be 04d? No, could not open path. I totally forgot how to do it. Let's go ahead and Google it. So how to turn images into video, ffmpeg. All right, so we have this here. I thought it was just, yeah, it's pick 04d. So I think I did it right. 060? Could not find path. Oh, that's because I'm an idiot. ls temp, I think it's image. Yep, good. All right, let me do that one more time. Should be 05d, but I forgot the image there. Okay. Unable to find output format for right. Out.mp4. Okay, so now if I do mpv out.mp4, what does this look like? Aha, okay, I remember this visualization. We did it a super long time ago. But yeah, this is essentially the visualization that I want to make, something like this. So let's go ahead and do control, I'm gonna go ahead and have that playing up in the upper left-hand corner on loop, just so again, we have something playing on stream. And again, the idea is that we want to generate something like that. And I'll explain what I mean in just a second. Oh, I just cannot use GUIs to save my life. Like, it's just hard. Okay, so we're gonna CD into project, simuleos, and then we're gonna go into ray tracing. L is here. ls here. It's in geometrical optics. And now let me do mpv out.mp4 loop 0. Okay, and we'll have this playing up here or something. I mean, yeah, we can just make it big, I guess. That's a really big visualization. Maybe we want to make it just a little bit smaller. I don't think people need the visualization to be that big, right? So maybe something like this, make it a little bit centered, move this up a bit. Sure, that'll do. Okay, so what are we looking at here? Let me go to this visualization. Let's make it full screen. What we're looking at here is a series of lines over here on the left going into some sort of lens, and they're being affected by the internal refractive index of the lens. So the idea here is that we have some sort of parameter that's scaling from like 0 to 50 or something like that, and as it scales, the refractive index of the lens on the inside changes. So here, again, it's some sort of sinusoidal function, and we can see that the rays of light kind of go all over the place, right? I'm sure I have a bunch of other geometrical lenses that we could have used. This is just the one that I had available at the time when I typed in make. So this is kind of similar to the visualization that I want to do today. Essentially, I want to make a visualization like this, where we have light coming in, and then it either reflects or refracts on the inside of the lens. So I think we're just going to kind of workshop what exactly we want to do here, and yeah, go from there. So we are going to cd back a directory, and cd into Raytracing. The Windows Manager is OpenBox. Okay, and over here, Control C, cd. Oh, we're already there, so let's just run Julia. And let's just go. Okay. So one thing that we can definitely do, right, is we can, let me think. How did I do this before? Probably what I did is I probably had some sort of ray that was moving forward with time, right? And then I probably saved. Ooh, what did I do? How did I actually visualize this? Probably what I did is I created a 2D array. That was probably going to correspond to not only how many rays I have on the y-axis, but how far the rays go on the x-axis. So the idea is we save 100 time steps, and we just let the rays move forward 100 time steps. So let's just go ahead and open up VI 2D. I'm going to call it 2D.jl. And let's think about things that we're going to need here to, again, recreate an animation much like that one in the upper left-hand corner. So I think what we're going to need is we're going to need some sort of struct. Okay. Which I'm going to call rays. I guess maybe just ray. Now, what is the ray going to have inside of it? By the way, asterisk obelisk, thank you so much for following. Really appreciate it. So what does a ray have inside of it? A ray has inside of it probably an array. So like some sort of time steps, which is going to be of type array. And I suppose this should actually be positions. All right. Which is going to be the position of the ray. And this is going to be of type array. And I'm going to say that the array is going to be of type tuple. I don't know if this is going to work or not, but it's going to be tuple xy. And maybe this will work. I don't know. Let's go ahead and try this in the Julia REPL. Does anyone ever spend a week trying to solve a problem only to figure out the solution is like 5 lines of very simple algebra? Yeah, but for it's like 5 simple lines of code or something. Yeah, everyone's been there. I feel like absolutely everyone's been there before. I mean, the truth is, what always ends up happening to me is I spend a whole week working on something that's like really cool and like something that I'm pretty excited about, like showing people. And then at the end, I end up just going with the easy solution. So rather than doing the difficult thing, I just do whatever's easiest at the time. And I kind of hate that about myself. I hate the fact that that I will typically go through and have like, I know what the right solution is, but I end up just doing the easy thing in the end because the right solution is always too difficult. So let me see what happens if we make this array of tuples. Does that work? So let me do A is going to be equal to array. Well, let's just do the following. What if we do this? 1, 2. Let's do 1 point, 2 point or something. Is that going to work? It's an array of tuple float 64 float 64. So what if I do push onto A and we push in a new tuple, which is going to be 1, 2 or something. Does that work? Yeah, it seems to work just fine. Good. Okay, so it's going to have a set of positions, and then I guess what I'm going to do is have a vector of rays, and each one of these rays is going to have its own set of positions. Okay, cool. So that seems fine. Now let's think about what we're going to do next. Let's do some math, shall we? So we're going to do journal, new page. I don't know what I just clicked, but I clicked something and it seems to have worked. I'm going to draw a circle. 1 second. So here's our circle, which is going to represent our lens. The idea is that we're going to have some sort of ray of light come into our lens. And then, assuming that this is a standard lens without any crazy refractive index, I'm then just going to have it do what lenses would typically do, which I think would be something like, oh, how does this work? It probably goes in like this, and then it goes out a bit more over here. So if we send in another ray of light that goes here, pretend that they're parallel, it goes in, and then it goes up here. And what you see over here in this area is something called spherical aberration. What that means is, it kind of means that if you funnel light through a sphere, what's going to end up happening is there's kind of a focal point, but it's not a perfect focal point. So what does this mean? We know we're going to need some sort of function which is going to be refractive index at some location, right? So I'm just going to call it refractive index at, and it's going to take some sort of refractive index function, n of r or something, and then it's going to take some sort of position. So we'll say position, and then the refractive index function. Okay, so we know that so that when we're inside the lens, we can do some weird refractive index things. Cool. We know that we're going to have a vector of rays. Right? Seems fine. Again, I'm not sure if we're indexing that right, but again, we're just gonna say we know we need a vector of rays. What else do we need? We need some sort of time stepping routine. And this is where things get a bit more complicated. So let's just kind of work it out and just do something simple, and then we're gonna come back and we're gonna make it easier. Okay, so time stepping. What do we need to do? Essentially, we know that we have this thing called is it Snell's law? I think it's Snell's law, which basically says the velocity. Oh, 1 second. The velocity of some component on the inside of a lens, the change in the speed of light, is going to be equal to sine of theta 1 over sine of theta 2. So the idea here is if we have some sort, I got these mixed up, I think it's 2 and 1. The idea here is if we have some sort of plane, let's say, here, and on the bottom side of the plane we have maybe glass, and on the top we have air. The idea would then be that light would come in something like this, and then it bends towards the normal as it comes out here. And we have two different angles. One, we have theta 1 on the outside, and 2, we have theta 2 on the inside. So the idea is we're basically constantly solving this simple differential equation with every time step. So how did I do this before? I think we said that the position of our ray of light, we're just going to say it's going to be called x, is going to be x plus velocity times time. Okay? And then we solved for velocity. We basically said the velocity 2 is going to be equal to sine of theta 2 over sine of theta 1 times v1, or something like that. So then the idea would be that at every time step, we're basically simulating the fact or imagining that we're hitting a new lens. And so the idea is basically we just update x like we regularly would, and we have some sort of velocity associated with the movement of that ray of light. So I think that should be good. Let's see, glad to see it's not just me. Yep. Again, guys, if you have any comments, questions, concerns, or anything like that, let me know. Siwi Yuri, thank you so much for following. Really appreciate it. So I think this will be like the most basic time stepping, scheme that we could do. Like, I don't even know if it counts as Euler time stepping. It's just incredibly basic time stepping. So that means that our ray should also have an instantaneous, velocity. So we're gonna call that v, and it's gonna be float 64. Actually, no, it should be again of type tuple of float 64 or something. And then we also need an instantaneous position which I'm going to call P. This isn't the best notation, but this is what I'm going to do. And then this is going to be tuple of float 64. So the idea here is that we have a set of all positions. Sign of theta. I might have gotten that wrong. Let's check Snell's law. Again, I'm kind of working off of V2 over, oh, okay, no, 2, you're right. It's the refractive indices that are changed. So in that case, what we can do we actually even need the angles here? So how do we know? Okay, so these rays are going to have some velocity. Okay, so let's just imagine that these rays are coming into the lens. And let's imagine that I was good at drawing so that these rays are coming in so that the initial velocity, the velocity is going to be equal to, we're just going to say v in the x direction and then 0 in the y direction. So it's just coming horizontally inward, right? How do we simulate that? How do we simulate the bending of light? I suppose, right, so we do know that the full Snell's law is going to be V2 over V1. That was a V. Let's try that again. Is going to be equal to sine of theta 2. You're right, sorry about that. Over sine of theta 1. And this is going to be equal to N1 over N2. Okay? So that means that the new velocity, So the new velocity, we'll say V2, is going to be equal to either sine of theta, let's try that again, theta 2 over sine of theta 1 times V1, or it's going to be equal to N2, N1 over N2, one second, times V1. Maybe we need a tangent to the circle. Yeah, so we could do a tangent, but there's a way to do this with just, I want to say dot products. Because a dot product is defined as A dot B is going to be equal to the magnitude of A times the magnitude of B. I think, isn't it cosine theta or is it sine theta? I want to say it's sine theta because I want to say we can just use a dot product for this. But let me Google this really quick because I'm really bad at this. Dot product magnitude. It's cosine, isn't it? So we must be using the cross product then, instead of the dot product. Yeah, so it must be, yeah, it is cosine. So it must be the cross product that we use. Let me see what we did in the C++ code actually. So let me open up a new terminal and let me just read the C++ code. I usually like reading C++ code, but maybe it was really poorly written at the time. So CD projects, simuleos, and then geometrical optics. L is here. vi geometrical.cpp. And let's see, what do we have here? We have finding the radius, all this kind of stuff. Refract. Okay, so here I have double C. So double C must be the speed of light. Is going to be equal to the dot product of negative NL. Why did I do that? And then we say double D, which is going to be the... What is D? Oh no, this doesn't make any sense to me. So if we're doing a refraction, reflection, I think we'll deal with reflection later. Let me just try to figure out this refract function really quick. Okay, so what is L in this case? We have a vector L, which is going to be the XY position. Okay, so N is a normal. That seems fine. We probably need a normal so we can figure out the angle, like the theta, in and out. L is going to be the light ray. This must be a velocity, not a... this must be a velocity. Now, why do we do vector negative n? And then we say double index of refraction. So we say double D is going to be 1.0 minus index of refraction squared. Let me just write this out in math terms. So I'm going to grab this, move it over here. We're going to make it a bit smaller. And let's just write out what we're doing here and see if we can figure this out. Okay, move this up a bit so you guys can see it as well. Okay, so what is this code actually saying? It's saying that we're first going to create some sort of variable C, which is going to be equal to the dot product of, I'm going to say it's the velocity of the incoming ray dot, well, okay, so it's apparently negative n. 1 second. Negative n, oh, that does not look good. Negative n dot L, where L is, I'm certain it's going to be the velocity, or, okay, we'll see what L is. So this is the first question. What is L in this case? But we'll figure that out in a second. So then we say D is going to be equal to 1 minus n squared. Ooh, this is bad notation. So this will be the normal. Okay, that's also bad notation. No matter what I do, that is bad notation. So we're just going to say big N dot L, where big N is the normal vector. So it's n squared, and then it's going to be 1 minus c squared. Okay. And then we say that if d is less than 0.0, we return just the vector here. This is probably a way for us to... Okay, I don't know what that is. So return index of refraction. So then the value that we return, so I'm going to guess it is the final velocity, is going to be equal to the index of refraction n times L plus the index of refraction times c minus square root of d times n. Okay, I have no idea what this is doing. Square root of d and then times the normal vector. This is some code. Refracts a given normalized vector L. Okay, I see. Based on the normalized normal n, and given index of refraction, where index of refraction is going to be equal to n1 over n2. Okay. I need to think about how this works, because I am honestly a bit baffled by this. So, first of all, what are n and l? So n and l are normalized vectors, which correspond to the normalized velocity vector, and also the normalized normal itself. So what I think we're doing first is we're finding c, which I would normally denote c as a velocity. I don't know if I wrote this or if someone helped me write this on stream. I feel like someone must have helped me write this on stream. So we have d is equal to 1 minus n squared times 1 minus c squared. That's fine. So d is equal to, well, no, actually I have no idea what that's saying. We could try to figure that out. I have no idea what this is saying at all, and I didn't leave a link for myself. Man, this is why you don't write badly documented code. So refraction function, I don't know. Let's just see what happens code. I have no idea. Maybe I Googled this, refraction. So here we have this, here we have that. Let's see, what do we have here? I was hoping that this would give me some sort of code. L is your light vector, light position, and point on the surface. N is the normal, so normally L and N are opposite. Right. So let's see, do they have a... Did I write this before? I feel like I should have written this before. Let me see what happens if we go to leios.github.io. And let's see what we have here. I did the invisible lens. Did I have any... I probably didn't. I didn't. Yeah, I didn't write about this at all. That sucks. Okay. Seeing polarized reflection. Let's see, what do we have? Let me just Google, let's search for refract. Okay, let's just go up from the bottom. Double N2, index of refraction, yep. Target refraction, blah, blah, blah. Our refraction factor. Polarized reflection. Yep. Refraction failure. This code is quite hard for me to get through, but that's okay. Keep going. Target refractive index. Yep, that's fine. Maybe I need to make it bigger so you guys can see it. Sorry about that. Let's just keep going. Refractive index. Okay. I did not see oh, calculate refraction. Okay, so that's his entire... Oh, no. That's his entire function. Ah, that sucks. Okay. Clearly, whatever I wrote, your refract function looks like an OpenGL, looks the OpenGL one. Maybe. Let's see. Refract. What do we have here? For an incident vector I, surface normal n, and ratio of indices of refraction eta, refract returns the refraction vector r. So we say k is going to be equal to 1.0 minus eta times 1.0 minus dot of n I. I see. Okay, but this doesn't provide any, like, it doesn't provide any documentation there. Oh wait, what is this? So we have f. We might have to do some reading today, guys. I mean, again, I have I literally have a PhD in like something optics related, but I don't remember this stuff at all. This is like completely different than the stuff I normally do. I'm playing an FPS idle game. Cool. Yeah, cool. Sounds fun. Okay. So what do we have here? Uniform matte. Page 404, by the way. Page 404. Oh. Well, it's on 408, 407. Yeah, how about we just read through this and I just download it and we figure it out. So we're gonna save that file. Okay. What did I save it as? I saved it as GLSL. Great. So let's just read through that and we'll figure it out. So I'm gonna move this back. I'm gonna make it big again. And then we're just gonna move this back over to this desktop and let's just read through that and figure it out. So we're going to CD into projects. And now I'm gonna run, actually CD, probably we wanna go into downloads. And now we're just gonna run Zernal PP in GLSL. Here we go. Okay, I'm gonna make it bigger and we're just gonna highlight things, read through it, try to understand it. That is our goal for today. Also, let me make this a bit smaller. Something like that. Cool, okay. Seems like we have a plan. Optics. Yeah, it's been a while since we did optics. Honestly, my stream used to be a long time ago. My stream used to be like entirely focused on computational physics. Like that's what I did. It's been a long time, but back then we used to focus on optics a lot. Like we did ray tracing, we did finite difference time domain. We did a lot of stuff back then. But it's been a long time since then. Nowadays, I kind of don't like physics too much. There's an amazing book called Raytracing in One Weekend and talks and has pictures for how refraction works. Yeah, so I think you might have given me that last time. The vortices? Oh, yeah, no, that was way after the computational physics days. If I was doing vortices on streams, I probably hated physics at that point. I was probably just doing PhD stuff. That was maybe 2 years after the computational physics focus. Okay. Yeah, so I understand how refraction works on like, obviously I understand refraction, right? So, like, no questions there. I do understand how refraction works, and I can write a refraction function. What I'm trying to do is figure out what I wrote a few years ago when we did this. Like, the last time I wrote this code was like 5 or 6 years ago. So I'm just trying to figure out how I wrote that code and why I wrote it the way I did. So I'm hoping to just read through this. Besides, it's probably good to read through this for everyone on stream. So I'm going to get the highlighter out. It's going to be pink. You guys are just going to have to deal with it. Okay. So refraction is the bending of light as it passes through a boundary between surfaces with different optical densities. You can easily see this effect by looking through the side of an aquarium or at a straw in a glass of water. Light bends by different amounts as it passes from one material to another, depending on the materials that are transmitting light. This effect is caused by light traveling at different speeds in different types of materials. This characteristic of a material is called its index of refraction, and this value has been determined from many common materials that transmit light. It's easy to model refraction in our shaders with the built-in function refract. The key parameter that is required is a ratio of the index of refraction for the two materials forming a boundary where refraction occurs. The application can compute this ratio and provide it to the OpenGL shader as a uniform variable. Given a surface normal, an angle of incidence, and the aforementioned ratio, the refract function applies Snell's law to compute the refracted vector. We use the refracted vector in a fragment shader to access a cube map to determine the surface color for a transparent object. Once again, our goal is to produce results that are good enough. In other words, we're not after a refraction effect that looks plausible rather than a physically accurate simulation. In other words, we are after a refraction effect that looks plausible. One simplification that we might make, is that the model of refraction effect is that we model the refraction effect at only one surface boundary. When light goes from air through glass, it's refracted once at the air-glass boundary, transmitted through the glass, and refracted again at the glass-air boundary on the other side. We satisfy ourselves with simulating the first refraction effect. The results of refraction are complex enough that most people would not be able to tell the difference in the final image. If we go ahead and write a shader that performs refraction, we will likely be somewhat disappointed in the results. It turns out that most transparent objects exhibit both reflection and refraction. The surface of a lake reflects the mountains in the distance if you're looking at the lake from one side, but if you get into your boat and go into the lake and look straight down, you may see fish swimming around underneath the surface. This is known as the Fresnel effect. The Fresnel equations describe the reflection and refraction that occurs at a material boundary and as a function of the angle of incidence, the polarization and the wavelength of the light, as the indices of the refraction of the materials involved. It turns out that many materials exhibit a higher degree of reflectivity at extremely shallow grazing angles. Even a material such as non-glassy paper exhibits this phenomenon. For instance, hold a sheet of paper or book so that you're looking at a page at a grazing angle and look towards a light source. You'll see a specular mirror-like reflection from the paper, something like you wouldn't see at zebra angles. Because the Fresnel equations are relatively complex, we made the simplifying assumptions that A, the light in our scene was not polarized, and B, all light is of the same wavelength, but we loosened this assumption later in the section. And C, it is sufficient to use an approximation to the Fresnel equations rather than the exact equations themselves. An approximation for the ratio between reflected light and refracted light created by Christopher Schlick is the following. Okay, so we say F is going to be little f, plus 1 minus f times 1 minus v dot n to the fifth. Okay, I don't remember this equation at all. In this equation, v is the direction of view, okay? N is the surface normal, and f is the reflectance of the material when theta is 0, given by the following. So we say f is here. Okay. So f is going to be equal to 1.0 minus n1 over n2 squared over 1.0 plus n1 over n2 squared. Okay, fair enough. Where n1 and n2 are indices of refraction for materials 1 and 2. Let's put this together in a shader. Figure 14.1 shows the relevant parameters in 2 dimensions. For the direction of view v, we want to compute a reflected ray and a refracted ray. Okay, so for the direction of view v, we want to compute a reflected ray and a refracted ray. We use each of these to access a texture in a cube map. We linearly blend the two values with a ratio we compute using the Fresnel approximations described earlier. Okay, so this is good. Okay, don't remember the computational physics. So this is good that it's actually, like, this should be relatively quick. So we should get to code pretty quickly. We already see the Fresnel equations here. So we already see the Fresnel equations. And then we see this, which was also related to what we saw in code earlier. So we're getting there. Let's see. We linearly blend the two values with the ratio we computed using the Fresnel approximations described earlier. So in the CG tutorial, Rendima, her name's Rendima. That's interesting. That's a very random name. In the CG tutorial, Rendima Fernando and Mark Kilgard described CG shaders for refraction that can easily be implemented in GLSO. The code for our Vertex Shader is shown in listing 14.1. The ratio of indices of refraction for the two materials is pre-computed and stored in the constant eta. A value of 0.66 represents a boundary between air and glass. We can also allow the user to control the amount of reflectivity at grazing angles by using the variable for the Fresnel power. Lower values provide higher degrees of reflectivity at grazing angles, whereas higher values reduce this effect. The value for f in the previous equations is also stored as a constant. Okay, the vertex shader uses the viewing position of the surface normal to compute a reflected ray. Okay, so let's just take these equations and let's work with them a bit. What I'm trying to do is bring this back to a velocity of some sort. So let's see, what do we have here? Let me see how we're actually using the refract function. Refract. Okay, obviously there. So what are we going to say? Refractive index, refract. Okay. Refractive index at, refractive index at, refractive index at. Okay, but where's our refract function? Refract. Here, let's see where it's actually used. So we say the vector speed is going to be equal to refract ln index of refraction. Okay, so here we know that this is returning a, this is going to be returning a velocity. And we only use it here in this function, which is for propagate and vector refract. Propagate, it's used here as well. What's the difference between this function and that function? So this is propagate, refract, and this is another function that is also propagate. Oh, it turns out it's probably just an if statement inside of here. So we do refract here, and then let's use set number. So we do refract is going to be 164, 77, 266. I feel like these are two different functions. I don't really care that much. Okay, because we're going to be rewriting it. So we know that this returns a velocity, right? So let's see, how does this relate to these equations that we have over here? I'm fairly certain that we're calculating this f value, and we're going to be using this f value. Oh man, I'm going to have to... rescaling in Zernal PP is such a pain. I'm so sorry about that. So let's scroll down. Okay, so here are the equations that we have again. Okay, so we say D is going to be 1.0 minus index of refraction times index of refraction. Okay, and again, these are the ratios for the index of refraction, times 1.0 minus C dot C. Okay, so how and why, where is this coming from? I don't know where this is coming from, actually. I'm going to have to think about this a bit more. Because this is not what I was expecting at all, honestly. Because again, we have 1.0 minus, we have 1.0, kind of like we have in here, minus index of refraction squared. Did I make some weird approximations here that I just completely forgot about? So we might have done a multiplication. We might have done a multiplication somewhere that I'm just like kind of forgetting. So how do we have 1.0 minus C dot C? So C here looks like... I just can't read this code at all. Let's just keep reading. Let's see what they do for their code down here. So they say we have some sort of ratio is going to be equal to F plus 1 minus F times the power raised to the Fresnel power. The Fresnel power here is 5. Ooh, this is way different. Why do we have so many different ways to do refraction? Let me Google this again. I'm just going to see if we have anyone that's doing refraction like we were doing. In fact, let me just go here, go over to the top, and let's go up here, and let's just say refraction in code. Introduction to Shady, how property handle refraction ray tracing. Yeah, of course, because this is all a pain in the butt. So they have refract, and we say eta is going to be equal to 2.0 f minus eta. We float, they're using a cosine? Oh, no, it's dot of this. And then they say float is going to be equal to the following, I times eta minus n. Man, again, I need some sort of physical description here. By the way, Nate Lift 151 and Axis 101 Love, thank you guys so much for following, really appreciate it. Okay. So maybe what we do is we just use the OpenGL version of this, because the way I see it is, at least here we can trace it back to some sort of code somewhere, and I just don't remember where this refract function came from. I really just don't. So let's see, C is going to be a dot product, so probably what we were looking for was some sort of angle, it would, you know, if we used actual, like, properly formed variable names, this would help a lot. We might be able to go back and look at the old Twitch streams. I probably was backing those up on YouTube during the day. So the ratio of the index of refractions was IOR. So let's go back to this formula that we have up here. So the formula says F. What is F defined as? F is defined as F is a reflectance of the material when theta is 0, given by the following. And basically, if D is less than 0, so I think D here would be our reflectance. And we're going to say if D is less than 0, we're going to return the vector 0, 0. Which is going to be a velocity 0, 0. So apparently, at some point, we just we just say, no, you're not moving anywhere. Let's write this out again. So I'm just gonna write out what we have. So again, we said that we had C is gonna be equal to negative n dot L. Then we say D is gonna be equal to 1 minus n1 over n n2 squared times 1 minus c squared. And then our velocity at the end is going to be equal to n1 over n2 times L. Let's see. Plus n1 over n2 times c minus square root of d times big N. Oh gosh, I just don't remember any of this. Maybe we just go back through and we try to figure it out. The Schlick equation F is to compute the amount of refraction and the reflection of the ray, but you can't compute the refraction of the ray with this. Right. D is 1 minus index of refraction times sine theta squared. D is equal to 1 minus index of refraction times sine theta squared. I'm not sure. Let's take a look. So we're gonna go back over here. These are way too big now. Let me see if I can make them a bit smaller. So we're just gonna shrink those, move them up here. Okay, great. That'll do. And then I can erase this up here, and erase that over here. Okay, so right, so we do know that sine squared plus cosine squared is going to be equal to 1 of theta, okay? So in that case, we could say that, and you're saying that D is going to be equal to 1 minus n1 over n2 sine of theta squared. Maybe. We're just going to have to figure this out. So what is C doing? C is a dot product between N and L, where L is the direction of the light and N is the direction of the normal. So if we're doing the dot product here, what we're going to get out is, so if we do the dot product of N and L, we're going to get the magnitude of N and the magnitude of L, which are both going to be 1 because they're normalized, cosine of theta. So then C is going to be equal to simply cosine of theta. 1. Yeah, cosine of theta 1. So this is the theta as we're entering the medium. So this is this theta. Okay. So then what we're saying, I see. So now I understand what you're saying. So now we're going to say D is going to be equal to 1 minus n squared. So it's going to be 1 minus n1 over n2 squared. And then this is going to be multiplying sine theta. Squared. something like this. Probably I should have done it this way. Let's try that one again. Times sine theta squared. Okay, so that's correct. So then, what are we returning for the velocity? The velocity. So okay, why are we doing this to begin with? That is because we know that okay, well, let's just see what d is for then. Let's try to figure out d then. So we're going to say the velocity is then going to be equal to n1 over n2 times L, which is, again, just the vector, the normalized vector for the light. And then we're going to say plus n1 over n2 dot c. And again, c is going to be basically cosine of theta 1. So we're just going to put in cosine of theta 1 in here. Okay? Minus square root of sine squared, square root of d, where d is going to be, so it's the square root of 1 minus n squared, 1 minus c squared. No. Let's draw that out differently. Yeah, we're doing vector math. That's what we're doing. So it's going to be n1 over n2 squared, and then we're going to do sine theta squared. So it's going to be square root of that dot n. Okay, so let's just figure this one out then. So I'm going to move this over a bit. Oh, that's not going to work at all. Maybe I need to do this. Okay, that's also not what I wanted. I was going to do this. Nope. Okay, that's not working. I'm just going to grab this whole box over here. And we're just going to move it over. Move it up there. Perfect. I was hoping for something more high level and descriptive. So d is 1 minus theta 2 squared using Snell's law. D is 1 minus theta 2. Oh, right, yeah, because we have sine 1, sine... Yeah, okay. So let's just keep working on this. Thanks, guys. So essentially, high altitude, we have some old code that is working for ray tracing, but I don't remember exactly how we got the equation. So we're going through the equations to try to figure it out. Okay, so what does this turn into? This turns into, again, it's going to be n1 over n2 dot L plus, so sorry that it's kind of a bit in the air right now. We're just trying to do some math. So, and then this is going to be n1 over n2 dot cosine of theta 1. And you said that d is going to be 1 minus sine of theta 2 squared. 1 minus... Why is it theta 2 and not theta 1? Anyway, I'll just keep doing this. So minus... and this is going to be minus 1 minus n1 over n2 sine theta. And then 1 plus n1 over n2 sine theta dot n. Did that help in any way? We can... No, I don't think that helped in any way whatsoever. Okay, so what's Snell's law again? We know that Snell's law is v1 over v2 is going to be equal to sine theta 1 over sine theta 2 is going to be equal to n2 over n1. n1 over n2 times sine theta 1 is equal to sine theta 2. Yeah, so I think... Right, okay, so the questions are which theta is which? Okay, so we know that this is sine theta 1 up here, and that's fine. So we know that sine theta 1, or cosine theta 1, I'm sorry, I'm really bad at this, that's cosine theta 1, which means d now becomes the following, sine theta squared, and then you're saying that d is now going to become 1 minus sine theta. So sine theta 2 is going to be equal to, yes, so d now becomes 1 minus sine theta 2 squared. You're right. Yes, that is definitely correct. So let's go through v again. And let's see what we can do. I'm going to redefine this. I'm just going to do this whole thing over again. And let's see what we got. So v is going to be equal to n1 over n2 dot L. Yeah, so we're working on, yeah, so we're implementing a two-dimensional ray tracing method. Legend Drum Runner, thank you so much for following, really appreciate it. Okay, so we're going to do that plus, and then this is going to be n1 over n2 dot C, okay, minus, and this is just going to be 1 plus sine theta squared, 1 minus sine theta. Actually, these aren't even squared. So 1 plus and 1 minus sine theta. Let me remove that really quick. And let's move this over just a hair to make sure it all fits. Go back over here, sine theta. And this is all going to be dot n, which is our normal vector. So n1 over n2 dot L plus n1 over n1 dot n1 over n2 dot C minus 1 plus sine theta 1 minus sine theta dot n. Because d is 1 minus 1, d is 1. Oh, I'm doing math wrong. It's a square root. Ah, sorry about that. I'm doing math really wrong. Okay. I was trying to do something tricky where I did this 1 minus sine theta squared, right? But that doesn't work exactly how I thought it was going to work. I thought it would work fine because I don't know what I was thinking, but clearly it wasn't working right. Dark Leader, thank you so much for following, really appreciate it. I tried to expand that out into 1 minus 1 plus, and for some reason I just got rid of the root because it's been a long time since I did any actual math. So yeah, I apologize for that. That was just wrong, what I wrote down there. And again, here's Snell's law, right? So essentially we know what we're looking for is v2. The variable we're looking for is v2. So that's equal to this v2 in here. And this is sine 2. Okay, so now we know sine 2 in here. We know sine theta. We know sine theta 2. Theta 2 is going to be equal to 1 minus. No. It's going to be equal to n1 over n2 minus sine. Times sine theta 1. Does that help us at all? I don't think it helps us at all n1 over n2 dot L. That equals v2? Okay, well what if we just plug that in for v2? What are you looking for? So again, we're looking for v2. I highlighted it in blue over here. So we're looking for v2. And we know that this in principle should also be v2 because we used these equations before. I'm just not seeing how these two are related. That's kind of what I'm trying to figure out right now. So what is n1 over n2 dot L? What does that do? So that's going to give us another cosine. And then we have cosine of, what's the expression for v1? Is that known? No, I don't think we have an expression for v1. Oh no, v1 is known. This L here is kind of our v1 expression. So this L here is going to be v1 over the magnitude of v1. And c in here is going to be cosine of theta 1. Cosine of theta 1. Is there a squared in here that I'm missing? Let's see. So we're saying we're returning the index of refraction dot 1. Did I even write this down? Index of refraction dot L, sorry, plus index of refraction dot C minus square root of D dot N. Yeah, okay, so I did write it correctly at least. Again, we could just assume that these equations are correct, but I hate doing that. That's not how I fly. So, okay. So we've got V2, V1, C. Okay, what if we exchange C? Again, here, we exchange C for the cosine of theta 1. Oop, well, that didn't work, did it? So what if we exchange C for the cosine of theta 1? Maybe that helps us in some way? Okay, so if it's cosine of theta 1, we could exchange that. No. So, okay, we have this old code. We know that this works for a simple refraction function, right? So what I did is I took this equation and I'm going back to try to figure out how this equation fits back into Snell's law. So we're going the other way around. Because obviously I could write a simple refract function that uses angles and all this kind of stuff, and that's fine. But I know that this one works, and I'm trying to figure out why it works. Yeah. On the other hand, we could just, I mean, if we can't figure this out in the next 5 minutes, maybe we just write our own refract function and we don't worry about it. Like, honestly, it's not worth it at this point. Yeah, maybe that's just what we do. Maybe we just write our own refract function. Because at this point, I'm not seeing how we made this at all, if I'm being honest. And we could just, okay, so let's go the other way then. So journal, new page before. Again, let's write down Snell's law. So we're going to say V1 over V2 is going to be equal to sine theta 1 over sine theta 2 is going to be equal to N2 over N1. Okay, so you have no idea where the code expression was derived. We derived it years ago, but I didn't keep the derivation. So that's why I needed to rederive it. So let's just make sure I did write down Snell's law correctly. 2, 2, 1, 1, 1. Yeah, okay, I have it flipped, but that's okay. Right, that's the thing as well. Okay, so now we're going to say, let's actually flip these around so it's easier on us. I'm going to do it in pink because, you know. So that was not pink. So V2 over V1 is going to be equal to sine theta 2 over sine theta 1 is going to be equal to N1 over N2. Okay, so this is, so we're going to say V2 is going to be equal to sine theta 2 over sine theta 1 times V1. Okay, easy enough. We know V1 coming in, so now we're going to have a line. It's going to be drawn here, and then we're going to have the normal vector drawn there, and then we have light coming in, so it's going to come in here. It's going to refract there. So now let's draw sine. So we're going to have theta 1, theta 2. Okay, so how do we find theta 1 and theta 2? Okay, so theta 1 we will know, but we don't know theta 2 because we don't know the new direction. So we cannot find theta 2. All right, so we're going to have to find some way to substitute in something for theta 2. Okay, so I think that was the crux of the problem that we were dealing with before. Great, okay. So I think because we don't know V2 and we also can't find sine theta 2, because again, we don't know this new direction vector, I think that's where a lot of the problems came from. So first, let's find sine theta 1. And so sine theta 1 is going to be equal to, what are we going to call it? So it's going to be equal to, again, some sort of normalized vector, which we're going to call L. Again, it's just a normalized, so L, so let's draw it over here. So we're going to say L is going to be equal to V over magnitude of V. Okay? Well, theta 1's kind of known. We're just going to, I mean, we don't want to use actual sine theta or anything like that. So we're now going to say that sine theta 1 is going to be equal to, and also n is going to be the normalized vector, is equal to normalized normal. All right, so it's just, that's what it is, a normalized normal. So now we're going to say sine theta is going to be equal to 1 minus 1 minus square root of 1 minus cosine theta squared, which is going to be equal to L dot n squared. And that should be it, because L dot n is going to be equal to cosine theta, the magnitude of L, and the magnitude of n, cosine theta. But both of these guys are 1, so then L dot n should be this, so that should be sine theta 1. Let me go down to this equation that we have down here, and I think that's what this is. So this is sine theta 1. Perfect. So we're getting there already. So you can express sine theta 1 as a ratio of the two distances. Yeah, I always wrote them with a hat to show that they have magnitude of 1. Don't know as Americans do the same. I don't think I've ever seen that notation. What I have done is I'll define, hats are usually defined for vectors. So like, for example, I would say that this is a vector, this is a vector. So, you know, vector, quantity. And so, for example, vector, these are all vectors. So we can notate it that way. So the hat would be a vector quantity, whereas the non-hat would be a scalar quantity. Okay, so now we have sine theta 1. But we don't have sine theta 2, again, because we don't know what V2 is. So how are we going to find that? Well, we have the ratio. So we know sine theta 2. So let's just write it down here. Sine theta 2 is going to be equal to n1 over n2 times sine theta 1. Right? And we know sine theta 1. So it looks to me like the velocity is going to be equal to n1 over n2 times square root of 1 minus L dot n over oh no, I have these backwards. Sorry about that. They're upside down. No, that was right. Yeah, n1, n2 over square root. That's not right. 1 minus L dot n times v1. So I know for a fact that's not right, because in this case, these cancel out. Oh, no, we're just showing Snell's law again. In that case, these cancel out, and now we literally have Snell's law again, which is going to be, say, v is equal to n1 over n2 times v1. But the problem with that is that this version of Snell's law will output, like, n1 over n2 is a scalar quantity, right? So this means if you multiply a scalar by a vector, you're going to end up just like making the vector larger or smaller, but that's not what you want to do, right? So you want to actually move the vector changes direction. So you have to show that change in direction somehow. So, okay. I think this is the crux of the argument. So let's go down here and let's see what was done down here. So, how do we even get a plus in there? Where is that plus coming from? Now I do know, like, again, the GLSL stuff for OpenGL used some form of, Fresnel equation stuff. By the way, Keldam, thank you so much for following. Really appreciate it. How did you get your sine theta expression? The sine theta expression was the sine theta expression, sine theta 1. I assume you're talking about this one. We know that sine theta squared plus cosine of theta squared is going to be equal to 1. And we know that cosine of theta is going to be equal to L dot n. Sorry. How does square root of 1 minus opposite equal sine theta? Yeah, so it's going to be, so that's why if we, so that means sine theta is going to be equal to the square root. So solving this equation, we know that sine theta is going to be equal to, the square root of cosine theta, 1 minus cosine theta squared, right? So that's how we got this guy. And then we said that cosine theta, rather, the magnitude of L, magnitude of N, cosine theta is going to be equal to L dot N, because that's the definition of a dot product. So that's how I got sine theta 1, by mixing these two equations together. I think, I'm almost positive this is fine for sine theta 1. Sine theta 2, I think this is a correct statement, but I don't think we can use it for this particular derivation. Okay, so I'm going to go back down here and let's see. So we said n1 over n2 dot L. Okay, so so we're saying that the velocity is going to be equal to whatever the old velocity was, whatever the normalized old velocity was, plus some sort of change in theta. So I think what we're doing is something a bit different. So what we said was, okay, I think we're doing something a little bit different. So I think what we're doing is we have, again, here's our light ray coming in, here's it reflected out. I'm actually going to draw another ray in here. And so what we know is the following. We know that this is theta 1, and we know that these two guys combined is theta 1, and this guy over here is theta 2, right? And we're looking for theta 2, in a way. In fact, we're actually looking for this velocity vector coming out. Assuming L is the normed direction of the ray, the dot product with n will give you the length of the adjacent side of the triangle with the incoming ray as the hypotenuse. Yes, I think that's kind of the route that we're taking now. So now we know theta 1 is going to be this big angle. And so now what we're going to do, and I think that's what we're doing down here, is we're going to remove part of, so n1 over n2 dot cosine theta 1. Where does that come from? Dot cosine of theta 1. So again, that's going to be, I feel like there's this equation that it's called the Lensmaker's equation. I don't know if this is useful or not. I'm just trying to remember it. Like, is this useful? No, this is not. I don't think this is useful at all. Lensmaker's equation is equal to this. The focal length of a lens in air can be calculated from the Lensmaker's equation. F is the focal length of the lens. Now, this isn't useful at all because we don't have a focal length here. It's not necessary. There's no way we can guarantee that all the light rays will focus on the other side. Okay, so, So, I am genuinely stumped. It's been a long time since I did any type of derivation. So let's just keep trying here. Again, I'm just trying to get it to look like this equation down here. So we know n1 over n2 which is the ratio, is the dot L. Could have done a number of different things here. So let's see, dot L. So what is L? L is going to be equal to the, L is going to be equal to the velocity of the incoming light ray is what we're going to assume. So I think what we did was the following. We said we have this equation in here. Wait, where are we? So we have this equation in here, V2 over V1. So now we're going to say V2 is going to be equal to... Nope, that's not going to work either. Oh my gosh. V2 over V1 is going to be equal to N1 over N2. So what I was thinking was V2 over... V2 is going to be equal to N1 over N2 V1, right? Look at the book fully, computer graphics principles for the refraction function. Computer graphics. So I mean, again, I think that they're going to have a different refraction function than the one that we have. Besides, I can't really look at this right now because I don't have. I mean, I guess I could. I'm pretty sure this is 184 pages. You said page 757. There's no way this is going to give us 757. What chapter? 259. Yeah. Okay, let's see. I mean, I guess I could like just kind of randomly find the book online, but I don't really want to do that. Not. Here's the PDF. Let's see. And you said 757? Wow, what is this nonsense? Why is it 2 pages? 757. I don't understand. How do I change the view here? Does anyone know? Let's see. Color space. No, this isn't what I needed at all. Can I drop a link? No, I think I found the book. It's just a matter of finding what you're looking for. It's 3rd edition. Yeah, so give the section and we can find it. Also, does anyone know why it's doing 2 pages here? I'm probably just going to open this up in my own CD downloads, wget this URL, because honestly, I cannot deal with that 2-page nonsense. Okay. They referenced a different book version. Right, so I was hoping that we found... Yeah, so give me just a second to download this. I hate the fact that I'm illegally downloading a book on my stream, but that's okay. It is what it is. 16.5.2. Oh, 16. Oh. There's a completely different... Am I on the wrong book? Computer graphics principles and practice. Don't say it out loud. Probably shouldn't be. Ocular, computer graphics. And you said it's called Refractive Transparency. Let's see what we got. It is not in this book. Refractive. Index of refraction, yep. Yep. Fresnel, that's fine. Yep. Yeah, so they're also doing the Fresnel equation stuff, but we didn't do Fresnel equation. That's the thing. Unless we did, and I just wasn't paying attention to it. But no, I don't think we did any of the... Yeah, I'm pretty sure. Unpolarized form of the Fresnel equations. Fresnel reflectance. Let's see, energy reflected RF times the incident energy. don't think we did the Fresnel equation. But also, why is their Fresnel equation different than the Fresnel equation in GLSL? Light ray reflectance transmits through an interface between media. Consider figure 26.14. So just so I get it, you're trying to get this to run fast on a GPU. I'm not even doing GPU right now. We're literally just trying to get something working right now. And I'm just trying to kind of suss out their index of refractions. So right now we have a couple different index of refraction ideas, and I have one that I know works because it's what we used before. But I don't know where that equation came from. And then as we look at other sources, we found like 3 or 4 different ways to basically find different refractive index or different refraction functions. And my question is, what do we go with? Do you need a coordinate-free equation? I don't know what you mean by coordinate-free. Is a... Yeah, I mean, it does rely on a Cartesian coordinate system, so, I mean, my answer to that would be no, but I don't know if that's exactly what you mean, because I feel like that means something specific, and I've forgotten what that means. Okay. Yeah, so we're not doing this at all, because we're not dealing with... Yeah, we didn't deal with it that way. So we didn't have a reflection core, like we didn't have some amount that reflected and some amount that transmitted, which is what you should do in ray tracing, but that's not what we did at the time. And so because of that, we had it either all reflected, rather we made sure all of it was reflected or all of it was transmitted, and we didn't have this half and half type of thing. Again, in practice, we should have something more like this. So I think in principle, yeah, I think in principle, we should just stop trying to get what we had working before working, and we should, yeah, we should just do it this way. So I think what we should do is we should actually implement what they have in the GLSL framework. And the reason I think we should do that is because this is freely available online, so people can read up, and we can go from there. So maybe that's what we do. Maybe today we just finish reading these guys and try to figure out how they do it, and then go from there. I found the explanation book on Stack Overflow when I typed refraction function GLSL explanation on Google. So in principle, this does the same thing. But okay, so here's what I know. I know that there probably is a way to just implement these functions, and it will probably work for our purposes. However, I also feel that because we're trying to introduce ray tracing and teach it from a more fundamental perspective, I feel like what we should be doing is we should be providing more information so that people can, or we should be providing something that's closer to what people do in practice. And here we have literally right in front of us GLSL standard for computing ray tracing of a refracted ray. And so I think that's what we should do. GLSL, I mean, like that's OpenGL. You can't do better than OpenGL for like an open standard for this type of stuff. So I think that's how we'll do it. So what we're gonna do today then is we're gonna finish reading through here and just see what they do, and then we're going to implement that tomorrow, I think is the plan. So let's just do that then. Okay, so the other thing too is they have an approximation for the ratio between the reflected light and the refracted light created by Christopher Schlick is the following. Let's just keep going. So the ratio of indices of refraction for the two materials is pre-computed and stored in the constant eta. A value of 0.66 represents a boundary between air and glass. We allow the user to control the amount of reflectivity at grazing angles by using a variable for the Fresnel power. Lower values provide higher degrees of reflectivity at grazing angles, whereas higher values reduce this effect. The value for F in the previous equations is also stored as a constant. Okay, the Vertex Shader uses the viewing position and the surface normal to compute a reflected ray and a refracted ray. The vertex position is transformed into I-coordinates. The reflect and refract functions both require an incident vector. This is just the vector going in the direction opposite of V in figure 1.14. Oh, 14.1. Okay, so this is V. So we have N is the normal, we have theta, we have the refracted ray and the reflected ray. So, right, so there's light coming in, it's reflected, or it's refracted. Okay, seems fine. We compute this vector I by subtracting the viewing position, which is defined at being 0, 0, 0 in the I-coordinate system, from the I-coordinate position and normalizing the result. We also transform the surface normal into the I's coordinate system and normalize it n. To compute the angle theta, we really need the vector v as shown in 14.1 instead of I so that we can perform a dot product operation. We get this vector by negating I. Okay. Sure. We plug the values into the Fresnel approximation equation to get the ratio between the reflective and refractive components. The values for I and n are sent to built-in functions reflect and refract to compute a reflected vector and refracted vector. These are used in the Fragment Shader to access the environmental map. The application that uses these shaders allows the environment map to be rotated independently of the geometry. This transformation is stored in one of OpenGL's texture matrices. The resulting rays must be transformed with this matrix to access the proper location of the rotated environment. Okay, so what do we have here? We have main, we have vec3 reflect, vec3 refract, float ratio. Here again, we have the ratio defined. We have refract. But again, it looks like they're just calling, OpenGL's inbuilt refract and reflect functions, which is not what I was hoping for, but they gave us the equations that we could work with. So I think that's okay. Yeah, maybe that's okay. So Fragment Shader for Fresnel reflection refraction. So we have main. So this is just the mixing of the colors. The Vertex Shader for chromatic aberration effect. Diffraction. Okay, I'm a bit stumped. So what I might do is I might take a step back, do a bit of reconnaissance, and try to figure out how we want to move forward here. I think we do agree, or I agree with my own opinion, that we should be going the GLSL way. Now, does that mean that we follow the textbook? Do we follow this particular page? Not really sure. So we're gonna try to figure that out. I realize we didn't write much code today, but we did a lot of trying to figure out how reflection and refraction work. And I think that's good. We just need to figure out exactly what equations we need to implement and go from there. So I think this is where I'm gonna close for today. And let's see, what do we have here? Let me go ahead and close that. Go over here to Simuleos. Let's see who's live and who we want to rate at the end of stream. We've got Strager, Tayoni, let's see, we've got, how about we do Tayonui, because they're doing math tutoring and we did a bunch of math today, so I think that's probably fair. So let's go and start the raid on Tayoi, oh my, I can never spell it correctly, Nui. Let's start that raid. I misspelled raid, so let's try that again. Raid. I got the guy's name right, but I misspelled raid. Oh, come on. Okay, let's just go here. Let's just grab that and grab this, close that, paste it over here. Perfect. Okay. And that will be it for today, guys. Thank you so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. We'll come back tomorrow where we actually get this code working. Again, worst case scenario, we just spent a lot of time working on it over the weekend to get it working. But yeah, I'm pretty happy with what we did today. We just have I have a lot of thinking to do off the stream. So thanks guys again, and I will see you next time. Bye guys.